Welcome everyone. We are the IAM3D, the Solar Water Harvester group. I'm Trevor Solorzano. This is Tomika, Walkin, and this is Daniela, Montero, and our faculty advisor is Alexandra. So I'll be taking you through a few the things we're going to be talking about. So we're going to go over the objectives, what our device does, what it's supposed to do. We're going to go over humidity comparison charts. This is essential to making the device work, understanding the atmosphere. We're going to go over all the components involved in our project. We're going to go over all the designs, our proposed design. We're going to also talk about the cost analysis, testing environments that we use, and also just the different design components and conclusion and recommendations. So an overview of the objectives. Basically, we need to create a 3D printed model of something that would be able to extract the atmosphere, the humidity in the atmosphere, and create water out of that. And so it needed to be 3D printed just to adhere to the competition that we were entering in. We needed the design to be lightweight, small, so something that could be portable, user-friendly, as well as something that can be used in a kind of a sporty environment. This is something that can create water for, let's say, like an athlete or whatnot. So also we wanted it to basically harvest the sun's energy, be able to charge the battery be able to charge the battery to power our device. So this brings us to our humidity charts. So over here on the vertical axis we have the temperature difference to create condensation. Over here on the horizontal axis we have the ambient air temperature, and each curve represents a different level of humidity. And so in order to create condensation, there needs to be a difference between the surface temperature of whatever it is, let's say it's a metal, and also the air temperature. So there's going to be a difference, an ideal difference. In order to just kind of like read the graph, let's say there was 50% humidity in the atmosphere, we go over to the line that says 50%, it's that blue curve, and we are able to determine, based on the ambient air temperature, which is in degrees Celsius right here, we're able to determine the temperature difference that we need in order for condensation to occur. And we built all these into the code that works in the device. So device components. Basically, this is a quick schematic. For the electronics part, we have the Arduino. We use the Arduino because it was for the sake of coding, it was easy for us to do that. We were able to basically power a band switch and a relay. We were able to also read readings from a thermocouple and a DHT11. These two devices read temperature on the surface of the fins that we were condensating the water on. Also, the DHT11 measures humidity and temperature of the ambient environment. So we also have the solar cell and the battery, as you can see here. So the actual water collector, the case is 3D printed. The cold fin and the hot fin orientation are on the outsides of the Peltier plate. The Peltier plate is the device that creates that temperature difference that we need. The fan on the right side of the screen there, it basically circulates the air, the atmosphere, through the device, through the top, exits through the side, and we also have, we also incorporate the fact that we need filters, we need to keep harmful, toxic, whatever substances that we don't want inside out of it.
So basically, we came up with 3 alternatives for our design. On the far left, we have the first one, which is vertical design. A pro is that it has a larger surface area for the fins due to its cylindrical shape. However, it provides an inefficient flow path due to the fact that the air enters from the top and exits at the bottom. The second design alternative is a horizontal design. A pro for this is it provides a higher intake of air because we were going to include 4 fans. However, it's a higher cost and it provides a lot more weight. The third design alternative, the pro is that it was the most efficient flow path that we found. Actually, it was the only design that had documented proof of this theory working. And the cons is it's a more complex design due to the fact that the air must flow in a So from the third design, we came up with 3 basic sub-designs to choose from. 3A, it only has one fan that it takes air from the top. It does not have an exhaust fan, which is a con. And it provides, and because there's no exhaust fan, there is a larger surface area for the heat fin. Design alternative 3B, there is an exhaust fan at the side, no intake fan at the top. A con is because of the exhaust fan, it provides less surface area for the heat sink. So it does not have that dispersion of heat with larger surface area for the heat sinks. And 3C, it has an intake fan and an exhaust fan. The efficiency for the flow path is basically similar for all 3, but the main con in this design is it does not allow the airflow may be too high to facilitate condensation. In our research, we discovered that condensation occurs more efficiently with still air. So basically, we decided to go ahead with 3B, which includes the exhaust fan and not the intake fan. We figured that this alternative would be more feasible in getting rid of the excess heat that tends to build up in the device, and also a slight change that we made was we eliminated a lot of the space between the top of the fan, and we made it a 90-degree angle between the subject.
So for the SolidWorks simulations, we decided to use SolidWorks 2014. So the first simulation was the airflow analysis. In here, we wanted to consider the pressure within the chamber. So here you see the flow path that we mentioned before. Through the left, the air is coming in, and through the right, the hot air is going out. So the simulation followed all parameters, and from there we were able to take the desired pressure within the chamber, which we have to have in consideration because we have also filters in the inlet and outlet as well. Then we do stress analysis. What happens if our case falls? So the first one is if it falls from the front. The second one is if it falls from the bottom. The third one is if it falls from the top over here, this part over here. And then the last two, if they fell from both any corners, top or bottom. So from our study, we realized that unless it falls in a corner, it's not going to break. The only thing it might happen is that it might bend, but it's not going to break. So our device is safe if it falls. For our thermal analysis, the same. Similarly, we use the parameters, the cold fin and the hot fin, and then we decide to put the enclosure as insulated. So the main thing we wanted to see in this simulation is that the hot air wouldn't conduct heat through the cold fin. That was achieved through this simulation. So through the simulation, there was no heat conduction from hot fin to cold fin. For our cost analysis, this is the breakdown cost analysis of all the parts that we use. So here we include the solar cells, the battery, all the electrical components, as well as the mechanical components, the heat sinks, the filaments, and the 3D printing case. So the final cost for a prototype is $250. However, the 3D printing case was a donation. Therefore, final cost was $130. However, in this, we didn't consider the 300 hours that we invested working on the whole research and development of this project.
So basically, we conducted 3 main tests for our device. The first test, we simulated high relative humidity and high ambient temperatures, which can be seen in the top right photo. The relative humidity ranged from about 70 to 80%, and the ambient temperature was about 40 degrees Celsius. In the second test, we simulated low relative humidity to low ambient temperatures, which can be seen in the second photo. The relative humidity was about 40%, and the ambient temperature was 30 degrees Celsius. And the third test, final test, was high relative humidity, low ambient temperatures. The relative humidity got all the way up to 95%, and the ambient temperatures range around 20 degrees Celsius. So from our results, we were able to have a successful test with high relative humidity and low ambient temperatures, like I said, up to 95% and 20 degrees Celsius. Approximately 100 milliliters of water was produced in 1 hour of our testing, and with these results, we were able to prove our theory. However, design changes should be considered to improve the yield because initially we wanted to be able to produce 1 liter of water per hour.
Okay. So for global design components, we use both the SA units and the US units. We also, as we mentioned before, this design is environmentally friendly. At the beginning of the project, we have to identify the audience for our product. So as we mentioned before, this is for outdoor athletes, either they're hiking or biking, and they all have water needs if they are away from water sources. We also create a bilingual user manual, English and Spanish. And this project affects everybody, it doesn't matter the culture, worldwide. For our design experience, we use different standards, such as FSCC for what is our solar cells, or ASTM for the things that we use, ASME for the competition itself, the ASHRAE for the air filter, and the NSF for the water quality.
So just to conclude everything that we talked about, so we covered prototype construction. This was a very successful part of our project. Everything was able to come out as designed. Everything that was added to manufacturing and whatnot. We also successfully proved the concept that it can happen. The issue, and we were able to obtain 100 milliliters of water in the hour that we were testing. So also introduced the fact that electrical components are very, a big part of what this thing can do, and so we have to be able to understand all the concepts. So it's not just, the mechanical engineering aspects of heat transfer and fluid flow, but it's also, understanding everything that it comes together to make it work. So also controlled conditions are needed to be able to, put together a substantial amount of data in order to create, decent results and be able to infer, how can we improve different things. Also, heat fin design is one of the biggest things that we were struggling with, but in the end, it was able to yield something. Now, what we want to do is we just definitely want to improve on either the size, the surface area, the type of material needed to extract the heat more efficiently. Therefore, that cold type can get colder and then more yielding of the fluid of water.
And for recommendations, in order to have more water, more yield produced, would be to increase the size of the heat sink, as Trevor just mentioned. That way, heat can be more easily dispersed. Increase the fan size and the speed of the heat sink. Use better insulation for the thermoelectric cooler, and provide improve on manufacturability so that there's not so much space within the device itself. Investigate alternative methods for cooling. One of the issues that we also had was with the thermoelectric cooler, because it both heat and cool simultaneously, and want something that just provides more cooling. And in increasing the inlet vent size, we would prevent recirculation of air and increasing the outlet vent size.
This concludes our presentation. As I mentioned before, we are the IAM3D team. We appreciate all the people that help us throughout this year. Thank you, Dr. Tremente, as our advisor, Richard Sicarelli with the cost analysis and the things modifications, Dr. Sukhanov for the ANSYS simulations, Andres Pena for the additive manufacturing of the case, as well as Noe Núñez with the Arduino coding. Thank you. We open the floor for any questions that you might have.
In your report, you said you were unable to harvest water.
Yeah.
So someone needs to go back and change that.
Yeah.
What happened? Why did it not work then and it's working now?
So by the time we submit the project, the paper report, we weren't able to do that. So we discussed it with our advisor and Dr. Tosunoglu, and they gave us feedback on how to improve our
So what did you do to improve?
So the last thing that we do is that we put the system in a cool environment and increase the humidity. The last test we did was very low humidity, so what we did is that we increased the humidity up to 95%, and that's how we achieved to condense water.
And also some minor changes were made to the harvester itself with regard to the size of the outlet vents. And this one is a little bit smaller than the one that we actually were able to obtain a successful result on.
So upon your report, because you've got an answer that you've got a better answer to. So strong beliefs, just make sure that's in here.
What do you think is the life expectancy of your device? How long do you think it can last?
So based on this heritage battery we have here, we want to definitely optimize this device so it's not so big and bulky, but as of now, this thing will last us about 6 hours based on the amount of energy consumption that it's going to that it will consume. This battery will last 6 hours, which is the ideal time, throughout the day in order for this thing to be able to, just collect water according to somebody's use.
But if I'm hiking a mountain and this is gonna last me for 6 hours, how am I gonna get power again to recharge the battery and then get 6 more hours out? Let's say
That's the main use of the solar cell. For testing purposes, we use a battery, and the battery is to store the energy harvest through the solar cell. So you have to carry the solar cell in order to charge your device.
So if you look at the dew point temperatures and the humidity on a normal day, how much water do you expect to collect?
Okay, so what we expected initially, we wanted to produce 1 liter per hour. However, at the end we were able to produce 100 milliliters per hour. So from this, we believe that if we were to improve more in our design and the parts quality, we'll be able to attain that, considering 95% humidity, regardless the ambient temperature. Because in our Arduino code, we have integrated all the dew points that we explained on the graph.
Did you test the water once you made or condensed water?
No, we didn't.